As we are in university and with young people, I just want to present quickly Renewable. I founded Renewable 20 years before, so it's a very old startup. And I was a researcher and professor at CNRS and professor at Polytechnic Institute of Grenoble. And at this time, it was not the fashion to create the startup. So it was very difficult, but today I think you have a better condition. Because when I speak with people and with the bank or the finance, I said, I have created startup. The start was very fast. The up was very long because we need also the regulation, etc. But I'm very happy that we were the first in Europe to speak about recycling of non-lead acid batteries. And today there is a regulation, there is a royal decree in Spain, there is European directive, but at this time we don't have any regulation, and I bring the batteries in the back of my car. So it was quite difficult. So renewable energy is today really the key for the sustainable growth, but the dark side is the environment impact and the resource, the availability of the resource. Because the engineers are very genius. When we said engineers, in the middle we have genius. So they always provide new ideas. For instance, like your friend, oh, he's not here. He took the bread from our mouth because we were very happy with the cobalt, and they invent the iron phosphate. Iron don't cost anything. So we don't have any value to take from the batteries. But we have to take account about the scarcity. So before speaking about recycling, I just would like to give you some introduction on the problematic of the recycling, sustainability, and resource conservation. The sustainable growth is first interaction between maintaining the current growth. You are all very happy with your Facebook and mobile phone, etc. So you don't want to go back, sure. But we need also to take account about environment protection, about the resource conservation, because if you don't have lithium, no more Facebook. And also, we have to continue to develop the growth, the equipment, the new innovation, but with acceptable cost for the society. That's very important. Otherwise, you could have a very good invention, just stay here, because it's not acceptable economically. And finally, there is very, very important part, which is social acceptance. You need that your invention or your progress must be acceptable by the society. And this is very easy. Equation. It's very easy. This, crazy. Nobody can make this at equation because the society behaves intuitive. For instance, you look at the situation of the, I don't know how we said in English, gas de schist. United States are making millions and millions of US dollars. French just published a decree against any research, but French increased completely nuclear plant. So, where is the logic? This you should take account about the social acceptance. Otherwise, your invention will be something very interesting to present to students. Stop. So, in order to have sustainable growth, you have to fit, which is quite difficult, several circles, which generally they don't touch themselves. It's very difficult. And this is the challenge for 21st century. Challenge to make environment protection with the money, with the finance world, which is not easy. So today the impact of the city is really very, very strong, and quickly a presentation. If we look 100 years or 200 years, at the beginning of the industrial era, we have, oh sorry, I don't understand what happened. The industry growth, very good, the population growth, but in the meantime, the raw material decrease, and with a little of delay, because the reaction of the pollution takes some years, the pollution start to increase. In the meantime, the increase of the population needs increase of food and water. If we continue with this scenario, what's happened is one moment the pollution will be very high, raw material completely decrease. If you don't have phosphate, you don't have fertilizer, then it will be complicated for the agriculture. You don't have batteries for the machine of agriculture. You don't have pump to extract the water. So the situation becomes very, very complicated. And then the food decrease, and the main result is the population decrease. In the meantime, if you have a climate change, then the water increase. Some countries like Sri Lanka or Bangladesh or south of France or Florida disappear. Maldives disappear. Please go very fast for a honeymoon. In few years, Maldives disappear. So the population decrease. And to fight this, there is only two parameters. The first parameter is to fight the pollution and the climate change. And the second one, to stop this curve of raw materials. And this is a really very serious scenario. It was ordered by United Nations. It's not just science fiction. So it's for this that now is not a country problem, but it's worldwide problem with the CO2, with the water, with the glass ice melting, situation of the dry countries. You see the last few months we have a lot of problem in Asia. And then from 30 years, it's not a problem of country, but is a United Nations country. And there is a lot of convention. And the last one was just last December. So the situation is really critical. It's for this that for the first time, the nation forget their antagonism and sit down around the table to find a solution. So the sustainability has two levers. The first one is the dark side. The dark side of all the product we have, each product has a dark side, unfortunately. Because all those products, you use them every day. The lamp, batteries, fluorescent lamp, tools, but in all those products you have a lot of heavy metals and you have a lot of health and safety and environment impact. Screen, fridge, mobile phone, or your mobile phone batteries contain cobalt, which is carcinogenic completely, but it costs $45,000 per ton. So this is the light side and the dark side. And this is valid for almost every element of the periodic table used on the modern equipment. So this is the dark side. We have to take account about the environment impact and the end of life. And the second problem, it is something we look like the problem of the oil, is the availability and the geopolitics All the people know the problem of oil, but today we have a big problem with the metals, several metals. For instance, two metals, very strange, but the tin and the silver are very, very, very critical today. Why? Because 25 years before, several organizations decide that the electronic will be free of lead. That's very good because the lead is poison, is contaminant. So they said no more lead. As I told you before, engineers, genius, they take only 2 years and they find a new paste, new welding paste. And the pastes are based on tin and silver and some addition like bismuth and indium. In the meantime, the electronic grows 1,000%, and then decrease of resource, and we have only for 17 to 18 years, if we don't make anything, by substitution or by recycling. And this is valid for several metals. Only one metal which very good, the iron. This means that if we don't do anything, that's very easy, we can come back to the Iron Age, and people survive from the Iron Age. But again, no more stainless steel, no more mobile phone, no more iPad, no more laptops. So there is a real problem on the availability of natural resources. And this is something without unit, but just we see the autonomy and the vulnerability, and you see except the iron and little aluminum, all the basic metals of the non-ferrous industry, stainless steel, cars, TV, electronics, are really in very bad situation. This is the availability general. And the situation is more complicated because there is also a problem in geopolitical distribution of the natural resource. For some metal, which are not very well known by the public, but they are really strategic. For instance, US owns 67% of the worldwide resource of the rhenium. Rhenium is strongly important on the electronic. Brazil, 90% of the niobium. Now niobium, now magnet. Now magnet, now wind machine. Chile, copper. Palladium for Russia. Catalyst for the cars. China is the worst situation. They own 80% of the tungsten for the lamps and 88% of the rare earth. You remember the crisis when they stopped to export the rare earth. There is a big problem, and also there is a complaint of Europe, Japan, and President Obama near the United States because he said that China has not the right to block the exportation of any natural resource. Because rare earth like yttrium, lanthan, cerium, praseodymium, europium are almost everywhere in the high-tech industry. Africa, platinum and cobalt. Australia. And the problem of the Chile, Argentina, and Bolivia own almost 81% of the lithium deposit. So each few country has the monopoly of some strategic metal. Except Europe, we have 400 kg of waste per year and per habitant, which is not a bad thing. It's waste, but you have to think that, all those metals are in our waste. For instance, when the car arrives at the end of life, the palladium or the platinum of the catalytic pot is here. The lithium and the cobalt of the mobile phone is here. So today, politically, we have to consider the waste not as fatality and as big problem, but as big chance. It's a resource of tomorrow. And we have to consider everything today. Everything we have to consider it as a resource. This, we have 800 kg per used car of iron ore, indium, zinc manganese, lithium cobalt. So we have to consider now those wastes with another eyes. And this means that countries like Europe, Japan and South Korea, for instance, they don't have mine, and they have to move from what we call the old mine, they have to move to the new mine. This is mine. This is mine and this is mine. So we have a new concept today, the urban mine. We have registered this word in 2004, and today it's a reality. So we have to consider our waste as resource of metals. But that's very interesting. Okay, the car is easily to collect the car, but to collect the batteries, the mobile phone, the watch also, or lamps. The first new mine, this is the old mine, this is the new mine. But definitively, we need the adhesion of the citizen to feed the new mine. We need regulation and education to catch those resources. So how to construct the urban mine for the city? We continue to consume, but we keep our waste, we stop burning our landfill, and we develop recycling, reuse, recovery, and we feed our consumption industry. This is the only one way. This means that we have to take every product from the cutter to the grave. In all the cycle, we have to follow our metals. And now, as we agree to collect, what kind of technology we have to use? Obviously, from thousands of years, the humanity is using always metallurgy. It's minerally old. But to use it for natural ore is very good. To use it for waste, there is some negative side. Today, we are not allowed to waste our energy for waste. We keep the energy for something more important. When we treat the waste, we have CO2 emission, we have other toxic emission. This means that metallurgy is not the sustainable way to recover the waste. And one of the main problems I would like to speak about is the dioxin problem, because today, when you burn any organic product, you heat and you have some chloride and some metals, definitively you produce dioxin. Dioxin is highly carcinogenic product. And it for this that the regulation is 0.1 nanometer, not microgram, nanograms per cubic meter. So the best way to avoid the dioxin is to avoid thermal process. So we have also the possibility to use hydrometallurgy, because also it was used for many years. And just to explain what is hydrometallurgy, it was already used for the mine to make chemical treatment, purification, production of metals like copper or nickel, salt, oxide. So today, we don't have to invent anything. We just adapt the technology of hydrometallurgy to stop the ore and to feed with waste. So we have already technology ready to treat in clean, safe, and sustainable way the waste. And now we can speak about the three segments. First, the battery segment. Battery segment has a really huge progress. This is 2 batteries in the year 60 in the house. There is only 2 batteries. In the year 90, we moved by 10. And today, I don't have sufficient place to put everything. The last one is a postcard which sing happy birthday and with small batteries. So everything today is batteries. So the consumption of batteries was doubled by 35. And in the meantime, the need of the batteries changed. And then there is a strong evolution in the metals from early stage of batteries to the battery of today. We start with 3 metals: zinc, manganese, lead. We wait 60 years to have new chemicals, nickel, cadmium, and zinc, mercury. And after we increase again. And today the pyramid is very, very high. We have almost from 3 metals, 25 metals. 25 metals to collect, to recycle, to feed the batteries industry. So it's a real challenge. And why we have to collect the batteries? Because, okay, this is generic view of one batteries. Batteries contain valuable metals like steel, copper, zinc, nickel, cobalt, etc., etc. So they are valuable metals with not a lot of resource, but the battery are source of environment and impact, and all the red product have some problem. You just have a look to the MSDS, to the safety data sheet, and you see one is carcinogenic, one is toxic, one is harmful, one is poison. So all the products contained in the batteries have negative impact. So if we collect the batteries, we answer to 2 problematic. First, we keep the batteries better than they go to the landfill or to the incineration. And the second, we stop the environment impact. So let's move to the mobile phones and the batteries of mobile phones. Today the situation is, we have seen this morning 500 million per year. Today we have 2.2 billion of mobile phones. This means almost 100,000 tons of batteries in the world. And the situation now in 2015, I don't have the exact value of 2015, but I think it was almost increased by 25%, because there is a phenomenon of tablet, Samsung, iPad, and the phenomenon of the double iPhone, double mobile. I don't ask you, but I'm sure that several of you have to. So the increase was, according to the OMC, almost 35%. So for the lithium ion, it's a real mine of resource. This is lithium ion batteries. We have the collectors. We can recover the collectors, copper and aluminum. We recover the carbon. We recover the metals, whatever is the chemistry, cobalt, NMC, manganese, nickel, or iron phosphate. Whatever is the chemistry, we have always cathodic material to recover. We have also the solvent and the lithium. So we can almost recover everything on lithium-ion batteries if we use the suitable technology. Obviously, if you use thermal process, don't forget that lithium-ion is organic batteries. If you use thermal, carbon burn, solvent burn, the aluminum is quickly oxidized. So the lithium is trapped into the slag. So you recover only the copper and those metals. So you have to choose the right approach. So the process we developed is, okay, this one is for the EV, but for the mobile phone, we don't use this step. This step is used because we receive EV. We have now 12 contracts with 12 producers. Our biggest contract is 150 tons with Nissan. So we receive a lot of pack, module, and cells. And we make electrical control, discharge, we dismantle, and obviously, as you presented, we are ready to work on the second life of the batteries. Unfortunately, I have to say here that you are lucky to work with Nissan, but I have to say this, we work with 12 producers. I am in confidentiality, I don't give the other name, but on 12 producers, only 2 accept the second life of the cells. The 10 others said, each battery entering to you, I want to destroy it. I don't want to find it to find again on the market, which is not sustainable. Because, as you said, we can use for camping. We have made an action in Grenoble. I have started a charity action with an association. We make batteries and we give to the people who have wheelchair, no motors. They don't have money to buy with motor. So we offer motors with Schneider and we offer the batteries. But 10 producers are against this, unfortunately. So maybe next workshop with the European Commission is to impose not only the recycling, but to impose the reuse of the cell or module which are good, because it's waste of energy and material. After that, we make room temperature physical treatment and chemical treatment to recover the valuable materials. So just to give you the long way we make, we develop first a prototype working under inert atmosphere, and we make a mechanical treatment. You know that if you open lithium battery, burn very fast. So this is the evidence that nothing burn, because we work on inert atmosphere and we control the temperature. And our process was success because we moved from 10 kg, this is 10 kg per hour, then we make chemical treatment. This just to show you, I cannot show you the line because there is something confidential. And then we recover, after leaching, we recover a solution rich in cobalt, manganese, lithium, and we recover the carbon. I insist on the carbon because it's a very important point, as said your colleague this morning. Today we are able to recover a carbon because it's very easy. We leach in acid. So acid dissolves everything. As a result, we have a very pure carbon, 99.91. And we have 2 carbon, the graphite you see here, as electronic microscopy pictures. This is the flakes of graphite, and this is the nanoparticles of carbon black used in the cathode. So we recover the 2 products. And you see here, this is the peak, typical peaks of graphite, and this, as low angle, it's a characteristic of something amorphous. The carbon black is almost amorphous. So we have the two fractions here. And to close the loop, we have made batteries with this carbon without separating between graphite and carbon black. We use it in batteries, and we obtain almost the same result than the commercial batteries. Very basic batteries for mobile phone, not for EV. But you see, whatever is the discharge, we obtain a very good product. As Europe is not producing carbon, we can have here, by recycling, a source of carbon to use it for very, very basic, low-price lithium-ion batteries. Obviously, I don't want to use it because I don't have the answer of the resistivity and the conductivity. I don't use it for the car batteries, but for mobile phone, laptop, something like camera, is no problem. And then, after that, we separate the carbon, and then we precipitate the cobalt. And you see here, this is rich cobalt hydroxide obtained by precipitation. The problem of the lithium now, because here we have, you see, we start with 36 grams per liter of cobalt. We precipitate the cobalt, we have 300 milligrams, but the lithium is still here. Then we can recover the lithium at the end. And I would like to insist, according to the question we had during lunch, the problem of lithium is really a big problem for the future. At the difference of the other product, the lithium is based only on 3 countries, not more, 3-4 countries. Bolivia, 0.02, which is almost nothing for the chemist, but people said that the Bolivia, it will be the Kuwait of the lithium in the future, with 0.025%. For us, chemists, is impurities, it's just water treatment, and they consider this as a resource. Chile, Atacama, 0.14, Argentina, and now there is some production in China, and that's all over the world. And for this, Japan and Korea joined their effort to catch the lithium in the seawater. Just to let you know, the concentration of the lithium in seawater is 1 milligram per cubic meter, 1 ppm. 1 ppm, because here there is some hot water going, and they are rich in lithium. If you go in front of Sevilla, don't worry, you don't find lithium less than 0.01 ppm. So this is a particular place, and now they invest almost $100 million to extract the lithium from the sea. So this is lithium obtained in our process. There is now peaks of other things, is 99.5%, and fitting very, very well with the technical market. We don't want to make new batteries, but don't forget that the lithium is used only in the segment of lithium batteries, 25%. There is a lot of other industry using for many years the lithium, not only the batteries. And the request technical concentration, because to make one battery, you need 99.99. We don't intend to make this. There is other people who know very well. But we can sell them this one, and they purify. And today, the cost is a little more than what said your colleague this morning, is 8,000 euro per ton. But 8,000 euro per ton, starting from South America. So there is cost, freight, and insurance, which change a lot. So, if I have 10 minutes more, I would like to speak about two other subjects on energy consumption and energy vector. First, the fuel cells. I don't make you a course on fuel cells, you know this very well. Just want to tell you that the fuel cells are not what we know before on the space or on the bus, but they are entering in several segments. And depending on the capacity, we have mobile phone, laptop, cars, bus. This bus is running from almost now 15 years in Chicago and Ontario. It's produced by the company named Balach, 15 years. So it's not just test. Spatial, and today, a new segment, which is the stationary segment using fuel cells. So we can arrive to 100 kilowatt, 200, until 1 megawatt stationary using fuel cells. So this you know very well, technology. So we have an experience which is very interesting. We win a call for tender from EDF. People who are in Enel, etc., they know very well EDF. They know very well as hard they are. So small SME against EDF. Believe me, it was. I was almost making again my PhD against jury. But we win. We win against EDF and GDF for European call for tender to dismantle 200 kilowatt fuel cells. Because they make European, it is a legislation. And the people comes from France, from Germany, from Belgium, and they offer, oh, this fuel cells looks like, okay, 10,000 euro. We give you and we take it. He believed that it is turbine or alternator or something like that. Then there is a lot of nickel and copper wire, etc. And then the call for tender was cancelled. And they contact us, and we know that this one is phosphoric acid using methane, reforming, desulfuration. There is some lack, some task of hydrogen. So we propose a real safe dismantling and recycling fuel cells. We were 4 times more expensive than the people, and we claim to take the platinum for us, and we win, because we know as electrochemists what is exactly inside fuel cells, and we obtain it. So we also one thing very interesting. They don't have a plan, they don't have map, they don't have conception. Because they buy it from US company, and the US company disappear. So the only one map we have is 3D map. Now think on the composition of the shift, reactor, etc., etc. So it was the adventure. We dismantle it. We find the reforming, the desulfurator, and the heart of the cell. Desulfurator is pretty, very, very nice. It's a bomb. People weld it. And normally in my life, in industry life, when you have something like this, you make screw. Under pressure, at least you can open the screw. You can open and see what is inside. It was welded. So we don't know what is, so we cannot cut. So we need to move this one to make the radiography to see what is inside. It's crazy. So there is now eco-conception. Because it's a fuel cell having more than 16 years. Finally, We dismantle it completely, shift, this one desulfurator, the WE, and the cell itself. Cell itself was very easy because it's Nafion, anode cathode, Nafion, anode cathode. So it was very easy to dismantle. We just wash phosphoric acid and then we recover the electrode. This is the electrode. And we find a few platinum. We expect 2 kg. We believe that we become rich with this fuel cell, and we find only 900 grams. This means that in the fuel cells, when you don't use it, the platinum, which looks very stable, escape. I don't know how, maybe during the washing or something. But we find only 900 grams, but we recover 900 grams of platinum. So the recycling rate was 88%, which is not so bad for 20 tons of fuel cells. Everything, almost everything, except the insulating material, which is gypsum and wood fibers, like not asbestos, but looks like asbestos. This, we put it on the landfill. Otherwise, everything was recovered and remarketed. To make the composition of the all fuel cells marketed in French market, and also after the analysis, we developed a non-metallurgical process. So we design ourselves our prototype, and then we start the treatment. We have a double shredder, first opening, second shredder, and we obtain the glass, the fine fraction, which is the active layer, silicon or metals, and the polymers. Polymers are always 2 polymers, one PVDF and one PET. And then, after refining the polymers, we obtain clean glass, polymers, metals, and active materials. Today, all 3 are marketed. Now need to separate here, because it's copper, silver, and tin. We just sell it as alloys. That's sufficient. It's not our business to go very far. This was qualified by Saint-Gobain, because you see our physical treatment give a very clean fraction. And this is a problem. So today, all those 3 give 75% of the solar panel, which is not so bad. So if we stop here, we fit with the European directive, because the European directive imposed 70%. However, the active material, besides silicon, okay, we can forget, it's not expensive. But if we have other active material, like copper, gallium, indium, selenium, then it's very important to continue the research. So here we are our pre-industrial step, and here we continue our R&D at pre-pilot lab. And today we have obtained, already we recovered the indium copper as alloys, and the gallium and selenium are lost. But we continue to work using a new approach, which seems very, very promising. We use ionic liquids to recover the metals. And now there is very, very good selectivity. So that's all. at this time. So here we will start soon in north of Grenoble, 1,000-ton facility, and we hope to start soon in Castilla-Mancha, the same. So, first conclusion, I think we are very happy to be in the waste today because as chemists, we look to the old alchemists who tried to change the lead into gold, you remember? Unfortunately, they don't succeed. But we believe that we are part, small part, of the new alchemist because we change the waste into gold. And it is true. This gold, but it's waste. So we can change the waste into gold. So we believe that we are the new alchemist. But for me, the most important conclusion is mainly that you are in the university. The most important is to think that when the resource will be finished, you will always have an idea about the innovation. And our best resource is this periodic table with those people which are, I am old resource, but there is very young resource. Unfortunately, terbium is toxic. I'm not gold, but it is for us the best resource is the human resource. And thank you very much.